Hi, in today's video we are going to learn about Bayesian's belief network, that is BBN. We will discuss also different Bayesian belief network types, terms such as hard evidence and soft evidence, and uses of Bayesian belief networks. So Bayesian belief network is considered, or it assumes, within a set of attributes. As we know, our data is nothing but collection of set of attributes which some test training data. And within that set of attributes, whatever probability distribution we have, that probability distribution can have conditional probability relationship as well as conditional independent assumptions also. So, Bayesian belief networks consider both kind of probability. First type of probability is conditional probability relationship, and second one is conditional independent assumptions. So, let us understand how Bayesian belief network works. So let us consider, we starts with conditional probability. Remember, conditional probability is nothing but probability of event A given that probability of event B is already occurred is calculated as probability of event B given event A is occurred into probability of A divided by probability of B. This is our basic conditional probability formula. So we will start with same formula only, but instead of event A and event B, we will consider an attribute A1, and instead of B, we are going to consider attribute A2. So as for some training data set, if we are given first attribute, that is A1, which is conditionally dependent on another event or an attribute A2, we can represent conditional probability of A1 given A2 is equal to probability of A2 given A1 into probability of A1 divided by probability of A2. So this is as simple as that. Now, as we know that probability of A2 given A1 into probability of A1 is nothing but a joint probability. So, instead of this particular numerator part, we are going to substitute joint probability formula. So, probability of A1 given A2 is equal to probability of A1 comma A2, that is nothing but joint probability, divided by denominator as it is, that is probability of A2. Now, let me take this component, that is denominator, on the other side. So, my joint probability formula will become probability of A1 given A2 into probability of A2. So, joint probability is this product. Now, if joint probability of two attributes or two event A1 and A2 is equal to A1 given A2 into probability of A2, if I want to write joint probability of three events or three attributes, it can be written as A1, A2, A3. And that can be substituted as probability of A1 given that both A2 and A3 happen, irrespective of their order, into probability of A2, A3. Now we all know that this joint probability can be resubstituted. That's why we will keep our first component as it is, that is probability of A1, A2 and A3 event is equal to probability of A1 given A2, A3. This is as it is, but instead of this formula we can again resubstitute joint probability, that is probability of A2 given A3 into probability of A3, which is being derived from our this joint probability formula. Okay, so using this formula, we have substituted another joint probability, and that turns out to be these two components. Likewise, if I have set of n events, that is nothing but probability of event A1, A2, A3 up to AN. Set of n events is there. So their joint probability can be calculated as probability of event 1, A1, given that all other events happen from A2 to AN, into probability of event 2, that is A2, given that 3 to N all events happen, into probability of A3 given that from probability event 4 to n all events happen. Likewise, probability of event n minus 1 event n minus 1 given that event an happens into probability of event n. So this is something called as chain rule. So just we have discussed this chain rule. I have rewritten this chain rule over here. As you can see, probability of event 1, 2 up to n is equal to given by this particular expansion that we have just discussed. Now instead of instead of this different events, let me substitute name of event A, B, C, D, E. So I will just rewrite this formula that instead of A1, probability of event A, given that probability of B, C, D, E, remaining all events, into probability of second event, that is B, given that all remaining events happens, that is C, D, E. Just a second, this is mistake. F will not come over here. So we will have C, D, E into probability of third event, that is probability of C, given that remaining events happen, that is given that probability of D into E, into probability of fourth event, that is D, given that remaining event, that is E happens, into probability of last event, that is event E. Now, this is something called, we have called this as chain rule. So let me write this. This is chain rule of Bayesian belief network. But what will happen when events are dependent or independent of each other? Say for example, events are as specified in this graph that event A is having dependency on event B. Event B is having two different dependency. It is on event C and E. But event D is only dependent on event C. It is independent of event E. So what will be the conditional probability of all joint events? So joint probability of all event, which is nothing but probability of A, B, C, D, E, is specified that probability of A given B. As you can see, on event A, only one event is dependent, that is nothing but B. So we are finding probability of event A given that event B is already happened into probability of B given that already two dependent events are already happened, that is nothing but C and E. As you can see from this diagram, B event is having its connection to C and E, that means C is dependent on B and E event is also dependent on B. That's why for event B in this formula we write that probability of event B given that C and E both are happened into probability of C given that D. As you can see, D is only dependent on C. So whenever we calculate probability of C, we will consider consideration of previous event, that is D, into probability of D. Now as you can see, D event doesn't have any descendants. So we will directly substitute probability of D into probability E of E also. As you can see, E doesn't have any descendants. So again we can directly substitute probability of E. So this is the modified chain rule for a given network. Let us consider if there is a variable A and variable B which are connected with a directed path. Now in this path, variable B is called as descendant of A. If I draw this diagram this way, if event A is there and there is an event B. Now over this event, if A is event which is nothing but an independent variable, B is also an event which is nothing but an independent variable. But if they are connected with a direct path, we say that B is a descendant of A or A is a predecessor of B. Now, conditional probability distribution of each variable provides the probability distribution of that variable given the value of its immediate predecessor. Okay, so what this is given that conditional probability distribution of each variable provides probability distribution. That means for D, if there is a probability distribution table given, if probability distribution table is given for D, then it must consider different outcomes of A. Okay, so say for example, outcome of A or event A can be, say for example, true and false. So over the probability distribution table of B, we must consider its event. That means A event can be true or it can be false. Now, independent event of B can happen, say for example, we can win the match, we can have draw of match, or we can lose the match. So these three outcomes are nothing but outcomes of B, which is having different probability. And this B, it must include all different possibilities of A. That is what our second statement means. So for example, if A is having only two outcomes, we will have two different values or two different probabilities of winning in case of event A is true and event A is false. We will have two different values of draw of match in case of A is true and or A is false. And we will have two different values of losing a match given that A event is true or A event results in false. So that is what it says, variable given a value of its immediate predecessor. So B's predecessor is A. So we must consider all possible values or all possible outcomes of A. Say for example, A has three outcomes. Say for example, output 1, output 2 and output 3. In that case, in B's probability distribution table, we would have three different columns. That is what our second statement means. So based on these two different statements, as you can see, the network is given, and over this network there is one root node which says that first event is that rain will happen today. So there are two different outcomes of rain today. It is the given event is true or given event is false. So for a root node, we have a probability that chances of rain today is 0.1 and chances of not happening rain today is zero point 0.9. Now this is the predecessor for two different nodes or two different events. So this arc says that this arrowed arc or arrowed value says that Tim is going to late for a class, which is a child node of a root node. We say that Tim is going to late for a class is a having predecessor that rain is going to happen today or not. So there are two outcomes of predecessor event, true and false. So whenever we make a probability distribution table of Tim late to class, we must consider these two outcomes of its predecessor. So as you can see, this is a node's conditional probability for Tim. Okay, so Tim can be late to class. There are again two different possibility. Either Tim can get late to class or Tim cannot get late to class. But we must consider its predecessor's output also, that Tim is getting late to class and rain is there. Tim is getting late for a class and rain is not there. Tim is not getting late for a class given that rain is there, and Tim is not getting late for a class and rain is also not there. So here we have considered two different outcomes of its predecessor. That is nothing but true and false, and node's own event Tim is late to class also has its own two different outcomes, that is true and false. So we have mentioned all different probabilities for Tim is getting late for a class. Likewise, we will discuss over the left hand side, Paul is getting late for a class. Now as you can see, this is the descendant of rain today. So it must consider different outcomes of rain today in its probability distribution. So when we say this is Paul's probability distribution, Paul is getting late to class, we have two different outcomes, either true and second one is false. But we also consider its predecessor's output or different outcomes of that event. So Paul can get late to class given that rain is true. Or Paul can also get late for a class given that rain is not there. That is, rain today's output is false. That is nothing but this value. Paul cannot get late to class given that rain is there is zero point 0.4 probability, and Paul is not getting late for a class given that rain is not even there is zero point 0.5. Now as you can see, from if you are coming from top to bottom, that when we are talking about Paul is late to class, there are two different outcomes of Paul. So two different outcome must always make a value, or summation of these probability should be always 1. Whether it is with first outcome of predecessor or whether we are having second outcome of an predecessor event. So in either case, when Paul is getting late for a class, Yes and no. Both probability summation is 1. In this case also, probability summation is 1. Over this side also, when we are talking about Tim can either get late to class or cannot get late to class. And that summation of two outcomes of an event is always 1. Similarly, for this column also, summation of outcome of a particular event is always 2, 1. Okay, so with this network, we are going to answer what kind of question? So first question that we have asked is that for a given network, that means we have to consider this network and their respective probability distribution. Over this network and given probability distribution, we have to find that if Tim is late for a class, what is probability that Paul will also get late for a class? Okay, so first try to understand what is the question. It says that Tim is getting late for a class. That means output of this event is true. We are asked that what is probability of this event to be true. As you can see, this particular event and this particular event are not directly dependent on each other. This event is dependent on rain today and this dependent on rain today itself. That means there are no direct dependency, but there is an indirect dependency. So how we are going to answer this question that if Tim is getting late for a class today, that is given that Tim is late today. And what is probability that Paul will also get late given a network and set of probability. So first of all, we are going to find out an unconditional probability of Tim is getting late to a class. That means we are going to find out that today Tim is late. Okay, so as you can see, Tim can get late to class in case when there is a rain and when there is no rain. So we know that Tim is late, but what is the probability of rain if Tim is late? That we have to find out, and for that we have to find out unconditional probability of Tim is getting late. So Tim is getting late to a class, as you can see here. Tim is getting late to class in case of rain also. That is Tim is late given it is raining into probability of rain. Plus Tim can also get late given that there is no rain. That is into probability of not raining. So as you can see from this table I can find probability of Tim is getting late in case of rain. That is nothing but this particular term, which is 0.8 into probability of rain. Probability of rain is nothing but zero point 0.1, this value. Okay, likewise I'm going to substitute Tim is late given it is not rain. So Tim is late, that is true, is the row that I'm looking into. But there is no rain is nothing but this particular component. That is nothing but zero point 0.1. As you can see, this 0.1 is substituted into probability of there is no rain. So what is probability of it's not raining? Is zero point 0.9. So here I will have 0.9. Now after doing a math, I am getting this value that 0.17 of probability Tim is getting late for a class. Now using this particular probability that I have substituted over here for my future reference, I will find the probability of rain given that Tim is late to class. Now I know that Tim is getting late to class, but what is probability if Tim is late of probability of raining? So probability of raining, I am going to calculate this way. Probability of raining given that Tim is late to class. I am going to find this conditional probability using Bayes theorem, which is equal to probability of Tim is late given that it is rain into probability of rain divided by probability of Tim is late to class. Now as you can see, this is in event A, this is event B. So this is nothing but our Bayes rule, probability of A and B. Is it clear? Okay, so this must be clear to you that I have used a simple Bayes theorem. Now what is probability of Tim is getting late that it is rain? So Tim is getting late provided that there is a rain is given in this table. As you can see, we have to find Tim is getting late, which is equal to true. Given that rain is there, that is nothing but zero point 0.8 into probability of rain, which is equal to zero point 0.1 divided by Tim is late probability, which is we have already found in our previous step. That is nothing but 0.17. Doing a math, we have calculated its value is 0.17. 0.47. So probability of rain given that Tim is late is 0.47, and the reverse probability of not raining given a Tim is late is 1 minus 0.47. So whether Tim is late or not, Tim is late is given. It might happen that rain is happening in that day, or it might happen that on that day rain is not happening. So probability of rain on that day when Tim is late is 0.47, and probability of not raining when Tim is late is 1 minus 0.47. Last step, we will find out the revised probability of Paul is getting late to class. So we will use the probability that we have calculated in our second step. Okay. So for raining, we are calculating or considering the probabilities this way. So what is the probability of Paul is getting late to class? So Paul is getting late to class. That means I am considering this outcome of an event as true. So it's sure that I am going to use these two values. Paul can also get late because of rain. That is, rain is also there. That output of raining today is true. Plus, Paul can also get late because of it's not raining today. That is 0.5 into not raining. So my equation will be probability of Paul is late given that it is raining into probability of raining plus Paul is getting late because of it's not raining into probability of not raining. So using zero point 0.6 value, that is nothing but Paul is late and rain is today into probability of rain. Now this probability of rain is not a in general probability of rain, that in every day what is the probability of rain is happening. We are finding this rain's probability with the respect to Tim. So this raining probability is nothing but raining due to Tim is getting late. So raining due to Tim is getting late is 0.47. That's why I have substituted 0.47 over here. Plus probability of Paul is getting late and there is no rain. Given that there is no rain is 0.5. That is nothing but your this particular value, which is 0.5, and probability on the same day when it is not raining, when Tim is also late, is 1 minus 0.47. So I have substituted this value, not this value. Okay. So these values are calculated and it turns out to be 0.55. So this is our answer, that probability of Paul will also get late on the same day when Tim is also late is 0.55. 0.55. Final answer is probability of Paul getting late on the same day when Tim is also late for a class is 0.55. In this particular example, we have used two different types of evidences. Unknowingly, what are those two different type of evidences? There are two different type of evidences, that is hard evidence and soft evidence. What is called as hard evidence? Hard evidence is nothing but an instantiation. That means from where a point, from an event or from node, from where we start calculating our probability, which is getting back propagated every time for finding another evidences, is called as hard evidence. And this hard evidence of a node is an evidence that states the variable is definitely in a particular state. So basically, when in our previous question, when there is a test said that Tim is late for a class is an outcome of a particular event or a value of a variable which is given is called as an hard evidence. And what is soft evidence in that case? A soft evidence of a node or an event is an evidence that provides prior probability value for a node. That means in order to calculate Paul will also get late to class, we have used the revised probability of rain and not rain, as you have remembered. It was comes out to be 0.47 and 1 minus 0.47. So these two values are nothing but our prior probability that we have used in calculation of our next hypothesis. So Paul will also get late to a class is not an example of soft evidence, but calculation of this event is done using something called as probability of rain. and that probability of rain was not actual probability. We have not used zero point 0.9 and zero point 0.1 actually. We have used 0.47 and 1 minus 0.47 into our calculation. So these revised probability is nothing but an example of soft evidence, and these soft evidences are always used with to calculate or to answer our final question. Now, what is the problems that are faced by this Bayesian belief networks? So, BBN networks face two different types of problem. First problem is that the network structure for a given training data cannot be directly available. We have to infer it from our training data. That means from a given set of data, it might be priorly decided that this particular training data follows a particular structure. Or it might also happen that we have to derive this complete network structure based on our training data. So that particular thing is needs to be exercised. That is the first problem that for Bayesian belief network. The second problem with the same network is that all network variables are eitherly directly observable in each training example, or some may be unobservable. That means if I say that I have to construct network model based upon some training data, then I can also, there is a probability that we will miss out some of the variable which are in actually they are dependent, but we fail to observe those variables. So there are variables which are dependent on some other event, but that cannot be inferred from a given training data. That means we can directly either observe that dependency, or we might fail to observe that particular dependency because the training data is quite complex. So these are the main two issues or problem faced by Bayesian belief network. Now, what are the different types of Bayesian belief network that do exist? There are basically three different types of network. First one is diverging, serial, and converging. Then example that we have already looked into, that is the first one, in which we have only one root node and its dependency is getting diverged or distributed among two different child node or two or more child node. It might happen it is getting diverged into more than two child node. Again, this can also get distributed into two different child node. That is also possible. So these kind of networks are called as diverging network. Another type of network is called serial network, in which we have serial dependency. That means root node is saying that it is going to get rain today, and because of this rain it might happen that water is getting logged in train station, and because of this event it might happen that Tim is getting late to a class. Now this is nothing but a serial dependency, and that is nothing but an example of BBN network. And a third type of converging network example, in which two different events outcomes are getting converged into one event. So there are more than one root node in this kind of network. As you can see, Tim is having swimming class and there is a rain today. So it might happen Tim is getting late for a class because of swimming, or because of rain, or because of both, or because of none. So outcome of this event is dependent on two different independent events which are not connected with each other in any case. So calculation of probability of dependency can be changed in either type of network. So always we are not going to follow same procedure for diverging, and similarly for there will be serial, and there is will be no same procedure that we are going to follow for converging network. So the procedure will be different in each case. Now, in what cases we are going to use these Bayesian belief networks? So different uses of Bayesian belief network is to find out the updated knowledge. As you can see, the prior probabilities are getting revised, which is nothing but states subset variable, which is nothing but depends on the state of another subset variable. So evidence is nothing but it is getting updated based on an evidence which is collected for some other different node. Second example we can use when we have to choose a value for a subset of variables or subset of some events or nodes in order to minimize some expected loss function or decision error. That means whatever the predictions that we are making, if it is dependent on some other event, then it is better to calculate using Bayesian belief network instead of calculating independent event probability. So an application of Bayesian belief networks are many, such as in biology, in bioinformatics, we can use in order to find a protein structure, and we can use gene regulatory network because some genes are affecting some other genes in some cases, but in other cases they do not affect. So all these things can be regulated and monitored and can be used in ML with the help of Bayesian belief network. Apart from bioinformatics, we can use this in medicines, forensic, document classification, information retrieval, image processing, and decision support system, sports betting, gaming application, and this list continues for many more. In today's lecture, we have discussed Bayesian belief network with the help of one example of calculating that. We have discussed different types of Bayesian belief network. We have also discussed two terminologies such as hard and soft evidences, and we have seen major uses of BBN into an application. Thank you everyone for watching this video. This is Munira Topia signing out.